next speaker,
Yeah, sure.
Ram Rao, who's one of the unsung heroes of polarization, and he'll be telling us about polarized dust emission. Who would have thought, yeah?
Hi, my name is Ramprasad Rao. I've been working on polarization and I've known Dick for a long, long time. And this is a picture taken, I think, at one of the BIMA board meetings long time ago. I don't know which year it was, and I think this picture was given to me by Leslie, maybe, I'm not sure who. And so you see Dick, one of the things that I really appreciated about Dick was how persistent he is. And some would say he's persistent, he's relentless, perhaps even nagging. I mean, to the point that polarization, whenever you design a telescope, you build a telescope, so it's important to consider polarization from the get-go. So it's important to consider polarization from the get-go. And at pretty much every board meeting, I mean, the couple I attended, there was always, make sure that polarization works and make sure that the instrument is ready to do polarization. So here's the usual cast of characters. There's Dick, Crutcher, Stu, Leo, Lee Mundy, as Lou Snyder back here. And some can even maybe see Jack. Can you guys see Jack? There's like a little bit of hair. I think that's probably Jack. so there's Jack out here, I think. And Dick Plambeck. And so polarization was very important. So I think even from the very beginning, to try to have polarization capability for BIMA was a very important part. So one of the things that Joseph Michael showed, some of the maps of trying to get from dust polarization to magnetic fields, that what we actually measure in the sky are Stokes Q and U. And then we convert those to determine what's the polarization fraction and what's the polarization angle. And so that's what we actually measure. So in order to go from that to what the magnetic field is, you've got to have some other theory. In this case, we've been using grain alignment, and we've been using grain alignment with rats, or whatever theory. I mean, we started with Davis and Greenstein, but it's been modified. So in order to go from the polarization angle and the polarization vectors that you see to move to magnetic fields, you need some theory in between. Okay. And so that's what we've done. So we've taken those and we've assumed that the magnetic field vectors are perpendicular to that, and then once we rotate it, then we can get what the direction of the magnetic field is. And so this is IRAS 4A, and this works, but you got to be careful that you remember that this is always a derived quantity. So at BIMA, when we first started, the main source that we first started on was Orion. And you might say, why Orion? Right? Obviously, it's the strongest source. And initially, when we were starting at BIMA, we had only 3mm receivers. And so we built 3mm wave plates. And Orion was, I think, the strongest source that we could see. And it's probably the only source that I think we could see in polarization at BIMA. So this was actually not BIMA observations, but single-dish observations, much earlier than BIMA. And so this is Gonatis. I think Giles is probably one of the co-authors in this paper, and Roger Hildebrand, that's that group. And so you could see that this is much larger structure, and this is Orion at 100 microns. This is with the KO. And so you could see that the polarization angles, polarization fractions in the middle start dropping. And so you get like very, very small values of the percentage polarization. So this was another single-dish observation. This was at 1.3mm, and this was Dan Clemens and this group, I think Clemens and Barbanes, and they also found that the polarization angles were very consistent, and that's something like this. But then in the middle, something strange was going on. So we wanted to investigate, one of the things we've heard is that there's this polarization hole in the middle. Is this really due to grain alignment or other theories, or is there really structure in the middle? And that's why we decided to observe this with BIMA. And so when we did this with BIMA, so we did two observations. We did at 3mm and 1mm. And so this is sort of the central region, so much confined area. And the blue vectors show the large-scale direction of the electric field. So I'm not showing magnetic fields here yet, but this is just electric field. So this is a large-scale direction of the electric field, and the polarization which was measured, which was shown. And so with BIMA, what we actually see is that the hole still continues in the middle. And not only is there a hole, there are missing polarizations here, that the polarization directions right in between are orthogonal to each other. And so there's something strange is going on. And I mean, if this is really true that the magnetic field, just switches direction from, being this large-scale direction to something like here, and then are all these vectors that we see here, which are completely perpendicular to this, significant? And so when we first got the 3 millimeter data, we didn't completely, we weren't ready to completely buy that this was what's happening. But when we got the 1 millimeter data and they showed essentially the same pattern, then we were more confident that what we were doing was right, because this was among the very first observations of polarization in using interferometric techniques at millimeter wavelengths. So the thing that at that point was that we weren't yet sure of the alignment mechanisms, because there was a lot of theoretical work on grain alignment being done at that point. Alex Lazarian in this group, and I think Roberge and so on. So there's a big effort on trying to understand grain alignment. And so one of the papers that we read and said that it's possible that you could have mechanical alignment. And so we thought maybe instead of magnetic fields being the cause for all of this, it's actually grain alignment that produced this alignment. And that's what we thought. So we went looking for magnetic fields, but then in the end, perhaps we had some grain alignment issues. So I figured that, okay, I'm going to skip this. High mass, regions which were more complicated, like Orion, were very complicated, and so perhaps it was time to move to some other sources, something much simpler, some low mass young stellar objects. So this is the second object, the second low mass star forming object, in which we see this very clear signature, some clear structure in the polarization. So this is, again, these vectors show you the polarization directions. So this is IRAS 16293b, 16293a and b. So it's a region of low mass star formation. There are two binary, possibly a very large distance separations, like 1,000 AU or so. So this is very large scale. And so what we see here is, again, a very symmetric structure in the polarization out here, but then a very smooth polarization directions out here. And then in this case, we assume that we had alignment via radiative torques and magnetic alignment. And then once we rotate to get the direction of the magnetic field, we do indeed see that there's actually an hourglass almost pattern right here. And so this was another source, which was a low mass star forming region, and we saw this hourglass pattern in 16293 source A. And so but in source B, we noticed that the polarization directions were almost like there was actually a twist following this, this ridge of emission, but it was very smooth out here, but perhaps there was a decrease in polarization. And so we wanted to see this at higher angular resolution with the SMA. And so this is what we had. So that Joseph Michael has already shown this. And so what we actually saw was in source B that there was actually almost like a toroidal pattern. So this is the contours represent the total intensity Stokes I, and the pixel map shows the polarized intensity. And here in this case, the vectors have already been rotated. And so we thought that what we saw was grain alignment, magnetic alignment, and so we could rotate it to get the directions of the magnetic field. And so what we saw was this almost a toroidal or azimuthal pattern. And so at that time, we thought maybe that what we were looking at was a simulation, was like a disk, and simulations show that you should probably get some sort of toroidal pattern. And that's what we thought. And so we figured the problem was that these SMA observations that were done were quite sensitivity was an issue. I think most of these vectors were just about 3 sigmas, and we had only about a few independent points. You can see the beam, that's horribly big, right? So we had maybe a few independent points, and so it was something difficult. It was we had just measured it, so we needed something. We needed a telescope which is much more sensitive, and obviously we had to move to ALMA. Okay. So this is what we got. So I'm really grateful to all the people at ALMA for doing this. For providing this polarization capability. And so this is the electric field in IRAS 16293b, right? So the direction of the polarization that you're seeing. And so what you see out here is a very complicated structure. And the thing is that it's just, there's a disk sort of in the middle, which is face on, but then there's got an envelope surrounding it. So the polarization structure is actually fairly complicated. So perhaps there's some kind of uniform field which it's in this direction, but somewhere in the middle, it's hard to say. You can see there's a bend in the polarization direction. So you can go ahead and flip it to try to get what the magnetic field looks like, and it looks very complicated. Right? So there's lots of structure out here, and the reason this is happening is that, so what you have are confusing effects. You have effects due to the envelope, and then you have an effect due to the disk, and so the polarization is produced by both. And so it's important to be able to separate this very well, to be able to separate the effects of the polarization produced in the disk, the polarizations produced in the envelope. And so we decided, okay, let's go and since ALMA provides so much imaging capability that we should be able to look at it with sort of even higher angle resolution. And so with ALMA, we're trying to restrict visibilities and so on. So try to be able to compare it with the SMA. So what we are looking at is just the inner portion of the disk. And so this is the SMA observations, this is the ALMA observations. And you can see very clearly that the ALMA observations do reproduce the SMA observations in some detail. So you can see the vectors here aligned, vectors here are aligned, maybe vectors here are aligned, and then possibly even this vector is aligned. There's some difference here. So possibly these are about 2.53 sigma detections. So there could be some, obviously the SMA observations had much lower sensitivity, but still, this is about 3 sigma, and this is like 50 sigma or something like that. So you could see that even across this huge improvement in sensitivity, we still had, the ALMA observations do essentially reproduce what the SMA observations see. So now to go back and then we want to look at what the polarization, what the magnetic field is doing on larger scales. Obviously, you had the sensitivity with ALMA to be able to do it, and it looks completely different, right? So what we thought we had was a toroidal configuration in the middle, now becomes almost like a radial configuration at the edges. And this is almost signifying that there's probably some kind of monopole, and obviously we know that that's not possible, right? To have like such a radial configuration in magnetic field. So perhaps something else was going on, and that we can't just assume that the polarization is entirely produced by magnetic alignment. And so that's not realistic to have such a monopolar radial magnetic field configuration. So then what else was happening? So at this time, as Joseph Mikkel pointed out, and there are a number of theoretical work being done by different groups. And so one of the options is to actually, so before we can understand this, we'd have to go back, and instead of looking at the magnetic field direction, is to go and look at the electric field direction. And so when we do that and just look at the direction of the polarization and the direction of the electric field, now what does this pattern remind you of? We've seen this obviously at in infrared wavelengths, optical wavelengths, etc. So this sort of azimuthal pattern in the electric field tells us that it's almost like a scattering dominated effect. So it almost looks like a very nice circularly symmetric pattern. The polarization at the middle is doing something strange, but out here in the edges, it almost looks like what we have is actually scattering. And there's a lot of theoretical work being done by different groups, Kataoka et al. And Jian Li's group. And so it looks like what we have is scattering. And so this is a model for a face-on disk. And so this is the ALMA observations that we have. This is just scattering alone, what the patterns you would expect. And this looks very similar to this. This is what you would have if you had dust magnetic aligned dust grain emission, and this is what you have. And so in this case, this was work done by Jian Li's group, Yang et al. And what they are finding, what they did was they took some amount of scattering and some amount of emission, and what you're seeing is a combined effect, which still looks more like it's magnetic aligned, but realistically what we're having is just almost all scattering dominated. So what does this tell us? Joseph Mikkel has already shown us that. So since our observations were done at band 6 with ALMA, which is roughly 1.3 millimeters, that means the grain sizes are quite large, like about 200 microns or something like that. And so that's what we have. And so this is the plot that Joseph Mikkel already showed. So what we are actually seeing is probably scattering. And so what we would like to do is to confirm its scattering is wavelength dependent, to be able to do it at different wavelengths. And we already have a proposal in to be able to do it at 3 millimeters with this object. So I started off by doing, trying to do Orion, trying to find magnetic fields, and we thought maybe there's no magnetic field, that the alignment was all produced by mechanical alignment. And then we moved to IRAS 16293b, and again I thought we would be finding magnetic fields, but instead it was scattering. I don't know what strike 3 is yet, but I think when it happens, probably I should move from magnetic fields to something else. So dust emission is a powerful tool, but you've got to be very careful, and you've got to consider all the other effects. I just want to thank, because Dick actually was very instrumental in ALMA as well. And so while we were taking a break from trying to fix some of the problems and trying to identify some of the issues in Chile at the ALMA site, we took a little bit of time off and looked around. And so Dick, thank you so much for everything. I've learned so much. I'm really grateful.
Ram, I hadn't seen the large-scale scattering profile. It's pretty awesome. But does that mean, so those models show that the E-vector scattering profile should be azimuthal,
yes,
right on the outside, and radial on the inside. Okay, so rewind, take your SMA data, which you say is a toroidal magnetic field,
yes,
rotate those back to E-vector,
yes,
and then you get
yes,
pointing toward the middle. So
yes,
are you, is it basically suggesting that 16293 is the same as HH8081 and has radial in the middle and azimuthal on the outside, so it's all scattering all the time?
I think it looks almost like that. There may be some other issues because if the disk is optically thick and then you also have that is not as circularly symmetric, there seems to be a slight offset in the peak intensity and the polarized intensity. So there may be some sort of regions where there may be more effective beaming and scattering, even inside. Right? It's not necessary that, so you could still have scattering effects, but it may be somewhat more different than what you expect. It won't be just a simple sort of radial profile, but it may be, wherever there is some clearing or something like that, that any asymmetries in the structure of the disk might produce something. Yeah.
All right, let's thank all the speakers.